Here's some problems, some selected problems from the ones you all tried in section 8.2. I'll start with, these are the numbers that I'm going to do right here. I'll start with number 11. I'm skipping the first, let's see, the first four problems, 1, 3, 5, and 7, are just tic-tac-toe, tabular integration. That's the easy stuff, so I think you're probably okay with that. Number 9 is a pretty straightforward one. Number 11 is where they start to get a little tricky. So that's where I'm starting. So we're trying to find the antiderivative of the quantity natural log x squared. So we need to make our choices. Tabular isn't going to work here, so what are my u and my dv? Sometimes you try and your first try doesn't work. It's hard to know, but I'm going to go ahead and say maybe this is like the natural log function, and that I should make the whole thing equal, the u equal to that, and then dv would just be the dx. So the derivative of that, using the chain rule, the derivative of something squared is 2 times something times the derivative of what's inside. And then here the antiderivative of dx is just x. So let's see what we got there. I'm just going to check this and see if I think it's going to oh, sorry, that's a du there. Sorry about that. uv, that's fine, of course. v du, the x times the 1 over x will cancel, and I do know what the antiderivative of natural log x is. And I'm going to use that fact a couple times in this video. The antiderivative of natural log x, which I think you have in your notes from this section, is x natural log x minus x plus c. So that's a good thing to, I don't know, I mean, it comes up enough that you might want to try to remember that. You can always just do integration by parts on that to get that result. So anyway, we can use that result here. So that means that my original integral is now equal to v u, or uv, whichever way you want to write that, minus the integral v du. So the x and the 1 over x cancel, and I have a 2, which is a constant, so I'm going to put that outside, natural log x dx, and then I know what this antiderivative is. That's equal to x times the natural log of x squared minus 2 times the quantity x natural log x minus x plus c, and you might want to just distribute through here. You wouldn't have to do that, but there you go. And you know, every once in a while, it's just to convince yourself that this is really working, it's really doing what we think it's doing. You might want to try to go ahead and take the derivative of this and see if indeed it gets you back to this, right? So here's our answer right here. And just to check, you don't have to do this for every problem, of course, but I'm going to do it here. So the derivative of this, I'd have to use the product rule. The derivative of the first is 1 times the second plus the first times the derivative of the second, and the derivative of the second, we've done this already, it's 2 natural log x times 1 over x, right? Minus, I'm going to have to do the product rule again on this. I'll let 2x be my first. So the derivative of the first times the second plus the first times the derivative of the second, and then derivative of 2x is just 2, and the derivative of c is 0. So somehow, I guess that's all supposed to just turn into this, so let's see if it works. Natural log of x squared plus, simplifying x times 1 over x, those cancel, so that's just 2 natural log x, and then here minus 2 natural log x minus x and 1 over x cancel, so that would just be minus 2 plus 2, and would you look at that, 2 natural log x, those cancel, minus 2 plus 2, those cancel, and sure enough, we get that. It's a pretty cool technique when you think about that, when you look at how complicated that is, and that it all simplifies back to this. So That's what, it just shows us all the product rule involved here, that's what this is. Integration by parts is the product rule backwards. It's usually, well, almost always, I think, it's product rule where lots of things that came from the product rule end up canceling each other out. All right? Number 13, I'm just going to squeeze in here at the bottom. It's possible to do this in a very difficult way, but if you just remember the fact that if you know the antiderivative of something and you need to find the antiderivative of a, instead of natural log x, a linear factor of x, then that's pretty easy to do. The derivative of this is just 1/3, right? The derivative of this inside thing. So when we read, the derivative of this is 3. So when I do the antiderivative, it's going to pop a 1/3 out. So it's almost like doing a u substitution, right? In fact, it is really doing a u substitution, isn't it? So we could say that's the same as the antiderivative of, let me write it out here, sorry. So if I let u equal 3x minus 2, then du is equal to 3 dx. So I need a 3 here, which means I need a 1/3 on the outside. So it's the same. This is exactly the same as 1/3 natural log u du, where u is equal to 3x minus 2. And hey, I know what this is, right? It's 1/3 times u natural log u minus u plus c. And then I just have to go in and put the u's, put the 3x minus 2 back where the u's are. And believe you me, that this is a lot easier than doing it from scratch. So 1/3 u, I'm just going to leave that 1/3 on the outside, u natural log u minus u plus c. There you go. So just wanted to show you that one in case you tried to do that the hard way. That is the easy way. Of course, to do it that way, you have to remember or look up that fact there. Let's see, what are we doing next? 17. We got antiderivative of tangent inverse of 3x dx. Now I'm going to do the same thing that I did before. I know that this is going to be an easier problem if I don't do it with the 3x. If I do I'm going to do this problem instead, and then I'm going to use the same trick that I just used on the last problem. So here u is tangent inverse x. That's my trig inverse. And dv will just be dx, so v is x, and hopefully you remember that that is 1/1 plus x squared dx. Right, so rewriting this, I now have that this original problem is equivalent to x tangent inverse x minus the integral of v du. And then this is its own little u substitution problem here. On its own, this is an easy problem. It might seem like a burden here appearing in the middle of another already complicated enough problem, but we'll just go ahead and plow through. So if I let u equal 1 plus x squared, then du is equal to 2x, right? I knew that that would work because the derivative of x squared is some kind of multiple of x. So that means I need a 2 here, which means I need a 1/2 here. So I'm going to just make sure I don't lose track of this on the outside here. Minus 1/2, and then now this is 1/u du, right? So now that's just x tangent inverse x minus 1/2. The antiderivative of 1/u is natural log u. If you're stressing out about the absolute value signs, you wouldn't need them here, right? Because this is always positive, plus 1, so no risk of even having 0 in there. And that is the antiderivative of tangent inverse. So now, if we go over here, we know the antiderivative of 3x is just going to be 1/3 times this thing with a 3x everywhere where you see an x. So that would be 3x tangent inverse 3x minus 1/2 natural log 1 plus 3x squared. Quantity 3x squared is 9x squared plus c. That's our answer. Right? You could distribute the 1/3 through there, but no big payoff for doing that. All right. So we're looking for ways to make this as easy as possible on ourselves. Anyway, 32. I better need a clean sheet here. So 32, we're doing a definite integral now. So let's see, from the square root of e to e, natural log x over x squared dx. So let's see, using Liate, this is the same, that's x to the -2, right? So I would still have to do my natural log first, and then dv would have to be x to the -2 dx. dv, I said. So the antiderivative of x to the -2, bump the exponent up 1 to -1, and then divide by the new exponent. That's negative x to the -1. Excuse me. Derivative of this is 1 over x dx. So my new version of this integral is uv, that's -1 over x times natural log x, and that's got to be evaluated from the square root of e to e. Don't forget about that. Minus the new integral v du. So that's -1 over x and a 1 over x, so that's -1 over x squared, or let's write it. Why would I want to write it like that? That's better like that. And you can see those two negative signs, that's going to cancel out to a positive. I'm going to go ahead and do that now. And I'm not going to evaluate this yet because I'm not quite at that stage yet. All right, the antiderivative of x to the -2, we just did that, right? Bump the exponent up 1 to -1, divide by the new exponent. So that is negative x to the -1. Right? You could consolidate those if you wanted to, because same limits of integration, right? So in other words, that's all the same as... You could also factor out if you wanted to. There's a -1 over x and a -1 over x. Let's get fancy there and do that. So -1 over x, factoring that out of both, times natural log x plus 1. Let me pause there for a second. Make sure you follow that simplification. Not necessary, but it might make things a little easier now that I'm going to plug things in. So first I'll plug in e, -1 over e. The natural log of e is 1 plus 1 is 2, right? Minus -1 over the square root of e times the square root of e is the same as e to the 1/2. So natural log of e to the 1/2 is 1/2 plus 1 is 3/2. So let's see, plus 3 over 2 square roots of e. I suppose you could try finding a common denominator. Let me just see what the book's answer looks like for that, and we'll see. Just make sure we're good. Yeah, they found a common denominator, all right. So let's just do that. So the common denominator here is 2e. So I'd have to multiply this by the square root of e over the square root of e, and they multiply this by 2, or 2 You wouldn't have to do this, but just for the sake of knowing that you're right and matching things up to the right answer, which of course we have to do sometimes when you do multiple choice. So that's that part over the common denominator, and then plus 3 square roots of e. So that's what the book's answer looks like. Not that you would know, because it's an even problem. But that's it. And if you had this form of it or something like that, that's good. I'm happy about that. And then the last one is an easy one if you take the same approach that we were taking before in the earlier problems, to try to take something that looks complicated and make it easier by using a factor that you already knew. So doing a regular old U substitution, that's just like a linear shift, right? When you do a substitution that's just x plus or minus something, it basically just shifts it. Du is equal to dx, so I don't need to mess with anything in there. All it does is change these from 1 to 3 now. And it should be pretty clear, I think, that the antiderivative, natural log x plus 2 from -1 to 2, is exactly the same as this. That's maybe worth pausing and reflecting on for a minute, understand what U substitutions accomplish. That's an easy example of where you can see, I think, what's happening there. And then I know from earlier problems that the antiderivative of natural log U is U natural log U minus U from 1 to 3. So plugging 3 in, I get 3 natural log 3 minus 3 minus 1 natural log 1 minus 1. Of course, the natural log of 1 is 0, so that term's gone. So it looks like I have 3 natural log 3 minus 3 plus 1. 3 natural log 3 minus 2. And that's it.